Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is ascents and descents. In this question, we're given a permutation P of integers 1 to n, and we define a permutation Q as the unique inverse permutation of P, which is like Q of P of I is equal to I. So for example, if this is a permutation P, then Q would be defined as. So at position 6, we'll place 1. At position 1, we'll place this 2. At position 2, we'll place this 3. At position 3, we'll place this 4. At position 4, we'll place this 5. At position 5, we'll place this 6. And now we define this f of p as the summation of these two terms. Now the first term is the number of ascents in p, or the number of indices I such that p of I is less than p of I plus 1. So for example, in this permutation, this index, this. These are the four indices which are the ascents in P, or the number of indices where P of I is less than P of I plus 1. And the second term is the number of descents in Q, or the number of indices such that Q of I is bigger than Q of I plus 1. So for example, this is one such position in Q where Q of I is bigger than Q of I plus 1. Now we are given two integers n and k, and our task is to find a permutation p such that f of p is greater than or equal to k. Now we're given just two test cases for this problem. The first is a sample test case where n is 6 and k is also 6. And in the other test case, we have n equal to 10 raised to the power 5 and k equal to 1.99 into 10 raised to the power 5, which is equivalent to 199,000, or we can also write it as 2 into 10 raised to the power 5 minus 1000, which is nothing but 2n minus 1000, right? We'll see why we wrote it like this, but this is just to represent it in terms of n. And yeah, now let us see the constraints. Yeah, these are just like either it would be both n and k would be equal to 6, or n would be this and k would be this. Now let us once see the sample input. So we are given n equal to 6 and k also equal to 6. And this is one such valid permutation. So in this permutation, we have four ascents, this, and this. And in this permutation, we have two descents, this one and this one. Right. So in total, f of p would be equal to 4 plus 2, which is 6, which is greater than or equal to k. And hence it is a valid permutation. Now let us see the solution. So first of all, let us see what happens in Q. Like how do we count these descents in Q if we are given a permutation P? Right, let's just try to make some observations here. So what happens here? So this one would come at this position one. Right. Now what would come over here at position two? This number, right? This 4 would come at this position two. Now what would come over at this position three? This three, right? Now what is happening is, like at position 2, this 4 is coming. At position 3, this 3 is coming, right? Now what would come at this position 4? It would be this 6, right? Now if this 4 is coming after this 3, then that means there would be an ascent over here, right? But if the 4 was somewhere over here, let's say the 4 was at position 2 and this 3 was at position 3, then this 3 came here, and then over here this 2 would have came, which would have created a descent, right? Now let's just continue building the permutation. So what is coming at position 4? This number 6. What would come at position 5? This number 2. Right. Now this created a descent. Right. Why? Because this 4 appeared after this 5. And hence, like at position 4, there was a 6. And at position 5, there is a 2. So there is a descent. Right. Now let us see what comes at position 6. It would be this 5. Right. Now in general, what we have observed is if a number I appears after I plus 1, it would create a descent in our permutation Q. Right. This is the observation that we just had. Right. Now, using this observation, can we say that if you're placing one somewhere, we should be placing two before this one to get a descent in our like the other permutation, right? And if we're placing two over here, we should be placing three somewhere behind so that this two, three also creates a descent in our permutation queue, right? So we can place a two here, we can place a three here, we can place a four here, and we'll just continue this up till some index. Let's call that index as b, right? Now it's time, like we have placed the numbers from 1 to some index b. Now we want to place the number b plus 1. What is the best index? Let's just place it over here. So this would create an ascent in the permutation p, right? Let's change the color. This would create an ascent in the permutation p, and these 1, 2, 3 are already creating descents. Now let us try to place this b plus 2 over here, right? So that this b plus 1 and b plus 2 creates a descent in the permutation p, right? And similarly, we should place b plus 3 here, b plus 4 over here, and b plus like dot 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 2b over here, right? Now we should place like 2b plus 1 over here. We can place 2b plus 2 over here, 2b plus 3 over here, 2b plus 4 here, and dot 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 till 3b over here, right? And we can just keep placing the elements like this, which seems like a pretty good like construction, right? Because all of them would be ascent, then these all would also be ascents, these all would be ascents in the permutation P, and in the permutation Q, these would be descents, these would also be descents, and so on, right? So it seems like it's a good permit, like good construction, but will this satisfy a construction, like will it satisfy constraints or not? Let's just try to see that once. So let us assume that b is equal to root n because that is a value which would maximize this, right? So we would have something like this: 1 b plus 1 2 b plus 1 dot 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 2 b plus 2 2b plus 2 and dot dot dot. And then in the end there would be b minus 1 2b minus 1 3b minus 1 and dot 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 b 2b 3b and dot dot dot, right? And this would be like the last element would be something like b square. And over here the last element would be like something similar. Now how, like what is the value that is being created? So we have, how many ascents do we have in this permutation P? So we have b minus 1 ascents in this part, b minus 1 ascents in this part, b minus 1 ascents in this part, and similarly dot 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 b minus 1 ascents in this part. And how many such groups are there? B groups, right? So what would be the total number of ascents? It would be b into b minus 1, right? So these would be the number of ascents in the permutation P. Now what would be the number of descents in the permutation Q? So we would have like this 1, 2, dot, dot, dot till B, right? So this thing would create B minus 1 descents. Now this thing would also create B minus 1 descents in the permutation queue. And so on, there would be B such values, right? So in total, we would again have B into B minus 1 descents in Q. Now what does this sum up to? 2B into B minus 1, right? We just add the number of ascents and descents. Now, if like b is equal to root n, then that would be equal to 2n minus 2 root n, which for constraints is equal to 2 into 10 raised to the power 5 minus 2 into 316, which is 2 into 10 raised to the power 5 minus 633, which would be greater than or equal to k. Why? Because k was equal to 2n minus 1000, right? Now, what if like this is the case which we considered for if b is like if n is a perfect square. Right, but if n is not a perfect square, let's say n is equal to 30, then what we could do is we can just pair up the first 25 numbers like this, then just simply place these 26, 27, 28, dot, dot, dot till 30 in the end. These might not create any descent in the permutation queue, but these would have like some number of ascents, which won't really matter because this number is already greater than or equal to k. Right, and this is pretty much the whole solution. The time complexity of this is going to be square root of n because you'll need to like create these groups and like square root of n plus n, which would turn out to be order of n only. Right. Now let us see the solution. So yeah, this is the solution in C++. So we're taking an input of n and k. We're defining the number b as square root of n. Now we'll append everything inside our answer. We'll start from I equal to b. So this is how the groups need to be created, right? We'll start with I equal to b and create all of them. So b, 2b, 3b. So while this like current element is less than or equal to n, we're just increasing it by b and appending it to our answer. Then we'll add for this b minus 1 and so on up till this 1. And then we'll be adding the remaining elements, which would be from b into b plus 1 to n if like n is not a perfect square. So this is pretty much for when n is not a perfect square. And then we'll simply print all of them. And now let us see the solution in Python. So we'll begin by taking the input of n and k. We'll append everything inside this list answer. We'll define b to be the square root of n and we'll convert it into an integer. We'll run a loop from b till 1. We'll define this current to be equal to b, and while this current is less than or equal to n, just append it to our answer and increase current by b. Then just append all the non-squares into our answer, like all the elements after b into b plus 1, to account for the case when n is not a perfect square. Then in the end, simply print our answer. And yeah, that's pretty much the whole solution. I hope you liked it. Thanks.